Okay, so for today, we will continue our lessons on the next topic. Okay, so let me share the slide. Okay, so the topic will be the temperature and heat. Okay, the temperature and heat. So next topic. Okay, in this chapter, sorry, this is not the topic. Okay, this should be the topic, right? Okay, so this is the units, the sub-chapter of this chapter, which is the temperature. Okay, we will learn about temperature and heat and the zeroth law of the thermodynamics. Okay, it's a part of the thermodynamics, but we will learn the thermodynamics in the last part of the chapters. Okay, so we will also learn about temperature and scales. Okay, we will highlight some of the thermal expansion that we have just learned last week. Okay, if I'm not mistaken, right? So we will also learn about heat and the mechanical work, the specific heat, and also the conduction, convection, and radiations. Okay, so let's start with the temperature and the zeroth law of the thermodynamics. Okay, so the definitions of heat: heat is the energy transferred between objects because of a temperature difference. Okay, when there is a temperature difference, so you can think you can when there is a temperature difference, like for example, from 30 degrees to 70 degrees, or 70 degrees to 50 degrees, so there is some a difference in temperature. So because of that, okay, it can create some energy transferred. Okay, so heat is the energy transferred between objects that have difference in temperature. So it's a quantity of energy. Okay, when we call or we highlight the energy part, so we need to know that heat is in joule. Okay, the units of heat is in joule because of heat is the energy. Okay, energy transferred from object because of the difference in temperature. Okay, objects are in thermal contact if heat can flow, okay, between them. Okay, we can say that object have a thermal contact. Okay, this is the terms for the contact. Okay, when object or one another object have been touched, okay, and heat can flow between the objects, so we can say that there is a thermal contact between the objects. Okay, so when the transfer of heat between objects in thermal contact ceases, they are in thermal equilibrium. So there is another terms in heat that we should learn about. This thermal equilibrium. Okay, the word is thermal equilibrium. Okay, because of there is some if there is a difference in temperature, for example, difference temperature, so it can create a heat transfer. Okay, between two objects, when there is a heat transfer, we can call that as a thermal contact. So there is a thermal contact. Then after the heat, okay, cannot overflow. It cannot flow from one body to another body. So we can say that both material or both objects have already achieved thermal equilibrium. So there is a certain terms that we should know when we discuss about heat. All right. Okay. So this is the zeroth law of the thermodynamics. Okay. What does it say? If object A, so this is object A. If object A is in thermal equilibrium with object B, okay, this is object B, this is A, and this is B, okay, this in thermal equilibrium. We can say that there is no heat transfer between A and B because it's already achieved the thermal equilibrium. And object C, okay, so then some object C is also in thermal equilibrium in object B. Okay, we can say A and B in thermal equilibrium, and if we take another object C and also achieve our thermal equilibrium with object B, so this is B and this is C, okay, new object, okay, we can say that object A, okay, without have a thermal contact with the object C, is also have a thermal equilibrium if they are brought into thermal contact. So we can say that A and B have a thermal contact, of course, because they have achieved a thermal equilibrium. Between B and C, it also involves thermal equilibrium. Okay, but C and A never touch each other. But we can say in terms of heat, okay, A and C have a thermal contact. So therefore, A and C also achieve a thermal equilibrium. Okay, so simple, eh? So temperature is the only factor that determines whether two objects in thermal contact are in thermal equilibrium or not. So we must say that if you want to know either the object is in thermal contact, in thermal equilibrium or not, we should look at the how or we should determine by looking at the temperature. Okay, heat and temperature cannot go side by side. It must comes together. Heat, whenever we are discovering heat or we want to tell heat, we need to emphasize on the temperature. So these are some scales in temperature. Okay, so obviously we have already learned about Celsius scale. So what is Celsius scale? We use the temperature in Celsius scale. We do a lot of temperature measurement in Celsius scale. Okay, but does it the only scales in temperature? Okay, so look at the Celsius scale. We have a water freeze at 0 Celsius. Okay, water boils at 100 degrees Celsius. If the water is a pure water H2O, it will boil at 100 degrees Celsius. Water freezes, this is a freezing point. Okay, and water boils at the 100 degrees Celsius is what's called a boiling point. Boiling point of water, 100 degrees Celsius. Okay, so there is another in a few countries, okay, especially Malaysia, we will use a lot of Celsius scales. Okay, for example, if we go to clinic, for example, the doctor will say that you have achieved 37.8 degree Celsius. So that means you are having fever. But in some countries, they did not use a Celsius scale. In fact, they are currently using Fahrenheit scale. So the Fahrenheit scale also have equals have some measurement, but in Fahrenheit. Okay, definitely Fahrenheit and Celsius is not the same. Okay, it must have some conversions, yeah, between Celsius and Fahrenheit. Obviously, okay. So water. Okay, if you look at the freezing of water at the freezing points, we can say that the freezing point of water is at 32 degree Fahrenheit. 32 degree Fahrenheit. Degree. Okay, degree. See, this is degree. Okay, then the dot. Okay, the subscript of O, there is a dot, a water freezes degree. That means the degree Celsius. Okay, so water freeze at 32 degree Fahrenheit while boiling at 212 degree Fahrenheit. You can say that between, if you look at the Celsius scale, okay, the difference between a freezing point and the boiling point is 100 degree. Okay, between 0 and 100 is 100 degrees. But yeah, according to the Fahrenheit scales, okay, the difference between Fahrenheit boiling point and also freezing point of the water is quite different because the water freezes at 32 while boils at 212 degree Fahrenheit. We can say that that's more than 100. Okay, so this is how they convert between Celsius and Fahrenheit. Okay, if you want to get the Fahrenheit scale, TF stands for temperature in Fahrenheit. Okay, with capital F, temperature in Fahrenheit. So 9/5 TC is the temperature in Celsius. Okay, there is a temperature. Okay, there's a temperature in Celsius and temperature in Fahrenheit. Alright, so 9 over 5 TC. TC stands for temperature in Celsius plus with 32. Okay, while if you want to convert from Fahrenheit to Celsius, so this is the TC, temperature in Celsius. Okay, 5 over 9 TF. TF is temperature in Fahrenheit. Minus 32, then you times with 9 over 5. Okay, normally, if you look carefully, if you want to convert from Celsius, Celsius is more less than Fahrenheit value. Okay, basically, if you look carefully, the Celsius a measurement or the degree in Celsius normally have lower value compared to Fahrenheit. So if you look carefully, 9 over 5 is already more than 1. Okay, 9 over 5 is more than 1. Therefore, if you want to convert from Celsius to Fahrenheit, that means from the lower value to a very higher value. So this is what you can say 9 over 5 here is the upscale or up value from the normal one. So if you times your temperature to 9 over 5, 9 over 5 is more than 1, so you can get more. So when you can get more, so that means there is a temperature in Fahrenheit. Okay, while the temperature in Celsius, it is more less than compared to Fahrenheit. So that's why when you have a temperature in Fahrenheit, you minus with 32, then you times with 5 over 9. 5 over 9 is not more than 1. Okay, the value is point something, point zero something. Okay, so when you times with the value, so you can get lower value. So that's how I can choose whether to convert from Celsius to Fahrenheit or Fahrenheit to Celsius. Okay, so this is the temperature conversions. Okay, on the one, find some spring day, you notice that the temperature is 75 degree F. That means 75 degree Fahrenheit. What is the corresponding temperature on the Celsius scale? So you need to convert from Fahrenheit to Celsius. So then you will use this kind of equation. 5 over 9, 75 minus 32 times with 5.9. So you will get 24 degree Celsius. So don't forget to put degree. Okay, because Fahrenheit and Celsius, you must put degree. You must put that a smaller O. Okay, on the subscript after the value, after the temperature value. Okay, if the temperature if the temperature on the brisk winter morning is negative 2 degrees Celsius, what is the corresponding Fahrenheit temperature? So, corresponding Fahrenheit temperature, so it's 9 over 5 minus times with negative 2 plus with 32, so you will get 28 degree Fahrenheit. Okay, so simple. All right, so let's look at this part, the absolute zero. Okay, the absolute zero. So what is the absolute zero? Okay, so you take a few guesses. Okay, you take a few guesses. You know that this is what we call as a Boyle's, if I'm not mistaken, Boyle's law, stating that okay, the higher the pressure, the higher the temperature, the higher the pressure. Okay, if you look carefully, all three gases, gas number 1, gas number 2, and gas number 3, follows the Boyle's law, which means when you increase the temperature, the pressure will also increase. So you can see that the trend is there. This is the trend of the higher the pressure, the higher the temperature. Okay, P and T is proportional. Okay, it increase proportionally. Okay, but that does not mean anything because at the 0 degree temperature, 0 degree Celsius, 0 degree Celsius, all pressure is not zero. Okay, all pressure have a certain value. So you can say that gas number 1, gas number 2, and gas number 3 did not come to the zero pressure. Okay, at 0 degree Celsius temperature. Okay, but how can we get zero pressure? Okay, how can we get zero pressure? So they do some extrapolation. Okay, they do some extrapolation to the all gases to know which temperature that have or that can achieve to the zero pressure. So they did some another experiments, okay, do some extrapolations, and then finally they will reach at one temperature. Okay, meaning that at negative 273 degree 0.15 degree Celsius, all pressure, all the gas from gas number one, gas number two, and number three, okay, all becomes a zero pressure. Okay, all becomes zero pressure at that particular temperature. So that means that's why all scientists will call that as the absolute zero. Okay, absolute zero. So the absolute zero means that all pressure at that particular temperature will be zero. Okay, so T equals to negative 273.15 degree Celsius. Okay, so that is some, and we should know that all the gases, okay, will have a zero pressure. That means no pressure at that particular temperature. So that's something else, or something can be taught in that particular temperatures. So what is the temperature? We call that as a Kelvin scale. Okay, Kelvin scale is similar to the Celsius scale, except that the Kelvin scale has zero at the absolute zero. So what is Kelvin scale? Okay, it is stated here that the Kelvin scale is similar to the Celsius scale. So if you want to do some conversion, you must start with the temperature in Celsius. Kita gunakan Celsius. Okay, as a how can we conduct or how can we get a value in Kelvin? Okay, if you want to know the temperature in Kelvin, you should come to the Celsius. Okay, Celsius is the main part. You can see that if you want, it started at the Celsius scale, you can measure Fahrenheit scale from Celsius, and also from Celsius you can measure Kelvin. So the the main contributions of Celsius is you can go to the Fahrenheit and you can also go to the Kelvin. So what is the value? Okay, so the Kelvin scale state that, okay, T equals to 0 at what? Okay, T equals to 0 at a negative 273 degree, 0.15 degree Celsius. Okay, that means at the absolute zero, okay, at the Kelvin scale start at, okay, 0 at the absolute zero. That means T0 for the Kelvin, it will be 0 at negative 273.15 degree Celsius. So that's why when we do some conversions to convert Celsius to Kelvin, so we can say that TC, temperature in Celsius, plus 273.15, then we can get the value in Kelvin. And for example, the Kelvin, okay, if you use Kelvin, okay, for example, if you want to know what is the temperature of Kelvin when the Celsius is 0, okay, for example, when the TC 0, what will be the value of the Kelvin? The answer is 273.15 Kelvin without degree. Okay, say no degree. Straight away you put K, capital K. Okay, capital K stands for Kelvin. And for your informations, the scale in Kelvin is the SI unit in temperature. SI unit in temperature. Celsius is not an SI unit. Okay, SI unit for temperature is Kelvin. Because when we say Kelvin, all scientists in the world can understand where is the value. Because some scientists around Asia may use a Celsius, but some scientists around Westerner, for example, you have the USA, okay, they will use a lot in Fahrenheit. So you cannot come to one you cannot agree to one particular temperature. So when they introduce Kelvin, so all scientists in the world may understand that okay, Kelvin is the SI unit. That's why it's chosen as the SI unit. There is no degree in Kelvin. Okay, there is no degree. You can put degree in Celsius, degree in Fahrenheit, but not in Kelvin. Just put 273.15 Kelvin. Just put K. Okay, so for example, if you want to convert a 55-degree Fahrenheit to the Kelvin temperature scale, you need to know. Okay, there is no direct conversions from Fahrenheit to Kelvin. So you need to do from Fahrenheit, you need to convert it to Celsius first, and then from Celsius you plus with 273.15 to get Kelvin. Remember, from Fahrenheit to Kelvin, there is no direct type conversion. Okay, so you need to convert it first to Celsius and then to Kelvin. Just simple, huh? You do some conversions, but directly, yeah, everything you need to through you need to convert it to Celsius first. Okay. Same goes if you want to convert it from Kelvin to Fahrenheit. From Kelvin to Fahrenheit, you need to convert it first to Celsius. Okay, convert it first to Celsius, and then from Celsius you convert it to Fahrenheit. So make the Celsius scale becoming your main criteria, or you becoming the center of your calculations, like this one. Okay, so let's look at this particular example. So the gas in a constant volume gas thermometer, okay, has a pressure of 80 kilopascal. kPa means kilo pascal. That means the pressure at 0 degree Celsius. Okay, for example, here is 0 degree Celsius. Assuming ideal behavior as in figure 16.3, okay, what is the pressure of this gas at 105 degree Celsius, which is here. So this is some uh, measurement that you can have whenever it's deal with the a graph of pressure against temperature. Okay, against pressure against temperature. So you can do some simultaneous equations. Okay, in order to get the pressure, because 0 degree you can get 80. What is this 105 degree Celsius? So what is the pressure? So you can do some sort like proportionally, okay, proportional equations in order to get the pressure at 105 degree Celsius. Okay, right. So this is the comparison between the three temperature scales. Okay, so from degree Celsius, you can look at the degree Fahrenheit, degree Celsius, but just Kelvin. So you did not have to put degree Kelvin. Okay, it's wrong. Okay, just put Kelvin. Okay, just put K. Okay, all capitals, degree Fahrenheit, capital F, capital C, and capital K. Okay, so the boiling of water 212 degrees Celsius, where is equivalent to 373. The 373 Kelvin. The freezing point 32, 0, and 273. Okay, the true value is 273.15, but normally they just put 273. Okay. Just look at the appendix whenever you want to do the calculations, because some appendix may put 273.15, but if the appendix just use 273, so you just use the 273, right, to convert from Celsius to Kelvin. Okay, you don't have to memorize all of this value, just pinpoint. Just do a normal one, which is the boiling point of water is at how many Celsius. Okay, what degree of Celsius. Freezing point is what degree of Celsius, for example. Okay, so therefore I would like to recap back, okay, some of our thermal expansion that we have just learned last week. Okay, For example, we have a linear expansion. Okay, what is the equation of the linear expansion? Delta L equals to alpha L not delta T. Okay, what is delta L? Change in length. Okay, change in length, because linear expansion alpha, meaning that you only do some expansion towards the linear part, just one axis. Okay, the linear part just one axis, that means on length. Okay, that's why we use alpha. L naught is the original length, and also delta T is the difference in temperature. Okay, right now you have already learned about temperature and scales. So you can look at the SI unit for alpha. Alpha have a Kelvin -1 or maybe Celsius degree -1. Okay, that means this one, okay, this one, okay, is the uh, value of alpha in Kelvin. Okay, this one is value of alpha in Celsius degrees Celsius. How this? Why is -1? Because when you divide with the when you times with the delta T over here is the difference in temperature. Okay, difference in temperature. So normally alpha value have is a Kelvin -1, but the question give you in Celsius. Okay, but I have already explained it. Okay, don't worry about the Celsius or Kelvin, because the delta T means change in temperature. So it's for example, uh, 70 degrees Celsius to 50 degrees Celsius. So this value, if you want to convert it to Kelvin, you will turn to X Kelvin and also Y Kelvin. Okay, I didn't want to focus on the value. Okay, just put X Kelvin and Y Kelvin. And X and Y Kelvin also, because the Kelvin and Celsius will have the same change in the same value, the same change in temperature. Okay, for example, if you measure in degrees Celsius, the value is 20 degrees Celsius, the change. Tolak lah, kan? Bahagi kita akan dapat 20 degrees Celsius. But if you put in Kelvin, the value will also, regardless of the X and Y value, it will also get you 20 Kelvin. So the delta T is the same. So that's why I didn't have to focus on Kelvin -1 or Celsius -1. Just use whatever they give you inside the appendix or the questions. Okay, don't worry much, alright? But the thing is, you need to know the difference in temperature. Okay, for example, in these coefficients of linear expansion, they use Kelvin -1. But in the question, they give you Celsius -1. Okay, so this we need to do some or you don't have to waste your time to convert it to Celsius to Kelvin. Just put the delta K in Kelvin. Okay, because it has the same value. Right? These are some concept. And from linear expansion, okay, right now we have area expansion, because it comes from the linear and also linear to linear, so it becomes 2 alpha. Okay, 2 alpha and A, because alpha times alpha will get you area. So that's why we call it as a area expansion. Okay, delta A equivalent to 2 alpha A. Remember to put 2. Okay, don't forget to put 2 alpha A delta T. Don't forget to put 2. Okay, the coefficient 2 is you must put it inside the area expansion. And then it goes to the volume expansion, because volume contains from 3 axes, x, y, z. So that's therefore it contains from 3 linear parts. Okay, but that one is for solid. Okay, volume for solid. Remember, when you have a volume, that means you have a container, and you can put anything inside that container. Okay, when you fill up with the fluid or liquid or gas inside the container, that means you must do it 2 times. Okay, 2 things at one time. Okay, the expansion of the container. Okay, because container is made from solid, and also the expansion of everything inside the container. So everything inside the container, if they are using fluid, then you need to calculate another volume expansion. So for volume, okay, be careful on this part, okay, because you can either just calculate a volume expansion based on solid, okay, but you need to also to cover or to calculate the volume expansion in fluid. Remember what is fluid? Fluid is liquid and gas. Okay, so for volume expansion, we will use 3 alpha, okay, as a solid. The change in volume is solid, and also beta, delta V, okay, delta delta V delta V equals to beta V naught delta T, the same, but they are using beta. Okay, but beta is what? Beta is the coefficients of volume expansion, but for fluid. What kind of value of beta here? There is no solid things inside this volume expansion. Okay, just use beta. Okay, right. So these are the value. Okay, we have already look at the examples of the value, the examples of the questions. Okay, you can use these examples to understand there is some value of 3 alpha and beta. Okay, you can have a difference in volume expansion between solid and also fluid. Okay, so let's go. Okay, so let's continue. Heat and mechanical work. Okay, so these are some experimental work that contains some heat that can be transferred to another form of energy. For example, because heat is in energy, okay, heat is energy, so it can be transferred to another form. Okay, in this case, we want to know what can heat can do. Heat can do from the heat energy or the energy to convert it to another work. Okay, so right, so we should know about one thing first. Okay, because whenever we discuss about heat, okay, the scales or the units that we use to understand heat is joule. Okay, so other terms can also be considered as joule is the kilocalorie. Okay, kilocalorie. You can find the kilocalorie basically when you having meals. Okay, for example, you can look at the back of the meals, or you look at the back of the container. Okay, the food container, it contains kilocalorie, the value of energy in another form. Okay, so 1 kilocalorie is defined as the amount of heat needed, okay, to raise the temperature of 1 kilogram of water from 14.5 degrees Celsius to 15.5 degree Celsius. Okay, that means 1 degree or 1 kilogram of water from to raise it to 1 degree Celsius. Okay, so you can say that 1 calorie, CAL, not calorie, is equivalent to 4.186 joule. Okay, 4.186 joule. 1 calorie equals to 4.186 joule. So that's how they calculated. When they eat, they know what values of energy, what measure, how much energy can be we obtain from a certain food intake. So that's how you can calculate it when you do some diet. All right. So the unit is in calorie and also joule. All right. Okay. Another units of heat. Okay, but this one is used by British, which we call as BTU, British Thermal Unit. Okay, the energy required to heat a 1 lb. lb stands for pound of water. Okay, because British didn't use much of kilogram. Okay, they used pound of water from 63 degree Fahrenheit to 64 degree Fahrenheit. Still about 1 degree. Okay, to raise a 1 pound of 1 degree. So 1 BTU, British Thermal Unit, is equivalent to 0.252 kilocalorie, and equivalent to 1055 joule. BTU is much more greater than compared to calorie. Okay, so because 1 calorie is equivalent to 4.186 joule. Okay, so you can know that 1,000 calorie. Okay, so you multiply, you will get 4,186 joule. Okay, 1,000 calorie is equivalent to 4,186 joule. Okay, but 1 BTU is only equivalent to 0.252 kilocalorie. So, but this one is kilocalorie. It's not 1 calorie, it's kilo. Okay, kilocalorie. Okay, so here you can know from BTU, British Thermal Units. Okay, you can have a kilocalorie, but in another forms of energy is joule. Okay, so look at the samples here. Okay, a 74 kilogram person drinks a thick rich 305. What is C? C stands for kilocalorie. Okay, C stands for kilocalorie, but with the capital C. Okay, they didn't want to put K char like that. They just put 305 calorie. 305C, milkshake. How many stairs must this person climb to work off the shake? Okay, that means to burn all the energy. So let the height of the stairs be 20 centimeters for each of the steps. Okay, 20 centimeters for each steps. Okay, so first of all, you need to convert it from 305C. 305C is not 305 calorie. That because calorie is 305 cal. Okay, 1 calorie is 4.186 joule. Okay, but this one 305C, capital C. Okay, so capital C means that K char. Okay, 305 K calorie. Okay, kilocalorie. What does mean by kilo? Kilo means 10 power of 3. Okay, 305 10 power of 3. That means 305,000 calorie. Okay, 305,000 calorie. So you want to convert it to joule. So 1 calorie equals to 4.186 joule. So you will get 1.28 10 power of 6 joule. Okay, right now we need to measure the quantity of heat, okay, or the potential energy there. That means mgh. So the quantity becomes mgh. Okay, mgh, you need to know your mass. Okay, g is the gravity and h is the height of the stairs. Okay, the height of the stairs. So from here, mass is 74 kilogram, and the gravity is 9.8 meter per seconds. divide with the 8.128 with this value. So you will get the height at 1760 meters. Okay, because you need to know how many steps, okay, how many steps that this guy should in order to work off, in order to burn all the calories intake. Okay, so the answer is 8,800 steps just to drink a milkshake. Okay, a very thick and rich milkshake. Okay, all right. So that will be a part of here. Okay. Um, I think I want to continue these things in the next part. Okay, not today. Next part. Okay, next part. Okay, the specific heat. But let's look at what does it mean by the specific heat first. Okay. So the definitions of specific heat is it takes 4,808 it takes 4,186 joule of heat to raise the temperature of, okay, again and again, heat to raise the temperature of 1 kilogram of water by 1 degree Celsius. It's all about, okay, it's taking what kind of mass to raise it to 1 degree Celsius. It's not easy. That's why we need to use a heat energy. Okay, so it's about 4,186 joules of heat to raise the temperature of 1 kilogram of water by 1 degree Celsius. Okay, so in other words, it takes 128 joule of heat to increase temperature of 1 kilogram lit by 1 degree Celsius. Okay, so there is some difference between, okay, object number 1 and also object number 2, because object number 1, okay, using water, okay, it takes about 4,186 joule of heat, with compared to object number 2, which is lead here, okay, it only takes 128 joule of heat. So there is some difference in the value. Okay, that means water contains a lot of specific heats, contains a lot of energy. Just to raise it to 1 degree Celsius, water will take about 4,000 something joule. With compared to lead, it only takes about 128 joules just to increase its temperature about 1 degree Celsius. So these two terms, that means, okay, we need to come with some definitions about specific heats. Okay, so the definitions of specific heat is the C equivalent to Q, that means energy, over delta T. Okay, definitions of heat capacity is just Q over delta T, energy per temperature. Energy per temperature is either SI unit in J over K or J over C degree. Okay, so Q is positive if delta T is positive, that is, heat is added to the system, and Q is negative if the delta T is negative, that is, heat is removed from a system. Okay, it's either the heat will be added to the system or removed to the system. So that's why after specific heat, we will learn a lot in terms of specific heat capacity. Okay, so since it takes about 4,186 joule to increase the temperature of 1 kilogram of water by 1 degree Celsius, it takes twice that much to make the same temperature to change it in 2 kilogram of water. Thus, the heat capacity of an object depends on its mass, a quantity which is property only on the material and not on its mass is the specific heat. So definitions of heat capacity is just C equals to Q over delta T. But in terms of specific heat, to pitch on the specific heat, now we need to add the mass, because we can say that when we increase mass, the value of the energy also increase. Okay, so when mass increase, it will also influence the energy. Okay, so that's why for the specific heat, we can say that the energy Q is equivalent to M delta T. Normally, okay, in your secondary schools, you will only use, okay, heat energy Q equals to MC theta, like this. The same goes to here, just use MC delta T. Delta T is for theta. Okay, that means theta, a change in temperature. Okay, so this is also the same, but this is why they want to know the definitions of the specific heat, the quantity of the amount of energy to raise a 1 kilogram of 1 degree Celsius. Temperature, the energy to increase 1 kilogram of the substance, okay, of the substance, okay, in this case water, okay, to increase it to 1 degree Celsius. So the correct definitions of specific heat is like this. Before this, we learned about specific. It's not specific. It's heat capacity Q over delta T only. Okay, but how can we put M here over here? Okay, because it is about definitions of specific heat. Okay, specific heat, meaning that it influenced by the mass. Because you can see here, okay, the heat capacity will depends on the mass. So the SI unit for the specific heat will be joule per kilogram Kelvin or joule per kilogram Celsius degree. Okay, degree Celsius of Celsius degree is just the same. So these are the specific heat at the atmospheric pressure. Okay, which contains, if you look carefully, the substance. Okay, from the part of, you can look here, this is water, ice, steam, okay, beryllium, air, aluminium, glass, silicon, and lastly, the bottom part will be in solid. Okay, and this part is more to fluid, and the fluid value is much more greater in terms of specific compared to solid. A solid will have the amount of energy to increase to 1 kilogram of 1 degree Celsius is less compared to fluid. If you look at fluid, okay, especially water, because it contains a very high specific heat. Okay, all right. So I think I will stop here. Is there any question?